Our last skill here in our 6th learning unit on acids and bases. Wow, I know this has been a lot. We are just piling and piling and piling these concepts on to understand a lot about acids and bases. So the good news is this last skill is going to be pretty short. It's totally qualitative, and it's asking or answering questions or answering things about 2 questions. How can we predict or know why a molecule is acidic? And then secondly, looking at how we classify and characterize things as acids or bases, and realizing that when we restrict ourselves to H plus or OH minus, we're pretty restrictive in what we consider something to be an acid or a base. So thinking about trends, right? Trends were something we looked at a lot in Gen Chem 1 when we talked about trends in electronegativity, trends in ionization energy, periodic trends, right? Scientists like to classify things with trends because that allows us to then explain and understand a system that's new. So we're going to do the same here with acidity. And this is a really important skill moving forward to be able to look at a molecule and tell why it's acidic or rank things in terms of acidity. So the question is can you really just look at an acid and tell how strong it is? And when we say look at an acid, we mean look at the chemical structure of the acid and tell how strong it is. Remember in our first skill when we were learning about acids and bases and how to classify something as an acid or a base, we identified something that had a proton, a hydrogen attached to a heteroatom was kind of what was necessary. So a hydrogen attached to an oxygen or a halogen is generally how we're going to see things that we classify as acids. And now we're going to learn in this last part of this unit, in this skill, why that's the case. So this is going to require us to kind of bundle some earlier skills, right? Some things that are critical to being successful in this learning unit are being able to take a name and translate it into a chemical formula. Take that chemical formula and draw a valid Lewis structure. And then from that Lewis structure, identify protons that would be classified as acidic, and then draw the conjugate base to evaluate and rank how acidic that molecule might be. So again, this is going to be relative comparison, identifying trends. We're not going to be able to get absolute numbers for how acidic something is, but we will be able to compare 2 things and identify this is more acidic than that. And that's going to be the extent of what we'll be able to do. So how do we do that? Well, basically, we are going to deprotonate an acid, remove the proton, and we're going to examine the conjugate base. The more stable the conjugate base is, the stronger the acid is that it came from. So there's a few things we can do to think about how we'd make a stable conjugate base. So let's look at kind of a general acid here, right? When we've got an acid that's going to be losing a proton, we're generating a conjugate base. Now, remember we said we have chemistry happen to generate weaker things? The weaker this conjugate base is, the more stable it is, the more that we're going to have an equilibrium that lies on the right, and the stronger the acid is that generated that conjugate base. So said another way here, molecules that are strong acids are strong because we can more easily break that HA bond, or as we'll see on some future slides, we can more readily stabilize the conjugate base. So here's 2 ways that we can more readily weaken or break that HA bond. So if we think about ways of weakening that HA bond, there's 2 ways that we've already learned about in trends from unit in General Chemistry 1, where we can think about the electronegativity of A. And so we can explain this acidity trend when we think about fluorine being the most electronegative compared to oxygen, then nitrogen, then carbon. And so fluorine is going to be then the most stable conjugate base, and it's also going to weaken that HA bond the most by having the most polar bond. We can also think about it in terms of bond length. The longer the bond is, the weaker it's going to be. And so that can explain the trend that we see with the hydrogen halide series, where the strongest acid is going to be HI because iodine is the largest atom. So we can use a lot of the trends that we've already had to explain some of the acidity phenomenon that we see. So these effects can also be cumulative, and we can also have effects from multiple sort of sources. So when we think about the electronegativity of A, when we have multiple oxygen atoms contributing to that phenomenon, that can help us explain this oxoacid series. So we have, for example, perchloric acid being the strongest acid in the oxo acid series. And so that has to do with the fact that multiple oxygen atoms can contribute to this electronegativity pull. And that also is going to be what weakens and polarizes this hydrogen-oxygen bond, and that's going to allow us to more easily break that bond, making a stronger acid. New concept to think about is really what we call electron withdraw. And you can simply think about this as the application of a bond dipole. We learned how to draw bond dipoles last semester. And so when we have this uneven sharing of electrons, and that's generally because of large differences in electronegativity, we can think about that in weakening this HA bond. And again, that's going to be from that electronegativity. But we can also think about it as this electron withdrawal can help stabilize the negative charge on the conjugate base. And this helps us explain the trend that we see with metals, why highly charged metals are able to create acidic solutions. So what happens here is we're going to have a metal that is going to coordinate to or bind to water molecules. And what happens is we are going to, because of that positive charge, kind of pull on the electrons in this oxygen-hydrogen bond. And not only is it going to weaken it, but when we have a negative charge that we have there on that resultant hydroxide ion, that's going to help stabilize that. So a lot of these processes sort of are overlapping and work together when we talk about electronegativity and dipoles and electron withdrawal. But all of them help to do two things: weaken the hydrogen conjugate base bond and also help stabilize that conjugate base after we've done that deprotonation. So the last way we can think about resonance or stabilization is through resonance stabilization. So resonance stabilization is the ability to delocalize electrons in a molecule and help spread out that charge. We learned about resonance structures back when we learned about drawing Lewis structures in one of the last learning units that we had in Gen Chem 1. And so when we can spread out that charge, that allows us to stabilize that conjugate base. So let's look at a series here where we're going to have essentially ethane, ethanol, and alcohol, and then acetic acid, a carboxylic acid. So we've already learned that carboxylic acids are really good acids, but now we're going to explain why it's so much better of an acid than, say, ethanol and then ethane. So let's imagine if we were to take ethane here, and we wouldn't even normally think about this as being an acid because it doesn't have a hydrogen that's attached to a heteroatom. But if we imagine deprotonating that, we would generate a negative charge that would live exclusively on this carbon atom. So not only is that not good because it's what we call a localized charge, but it's putting a negative charge on a not very electronegative atom. So this is going to be the least acidic of these molecules. When we now attach that hydrogen to a heteroatom, such as when we have this alcohol in ethanol, when we deprotonate that, that's much better because now we're putting that negative charge on a more electronegative oxygen atom. It's better able to stabilize that negative charge. But the problem still is that we've got localized electrons. That oxygen has to stabilize that negative charge all by itself. Once we move to the next category and we have our carboxylic acid, this is the most acidic in this group here, because when we deprotonate it and we generate this conjugate base with a negative charge, we can resonance stabilize that negative charge onto the other oxygen atom. And because we can spread out that charge, that's stabilizing. We've created a more stable conjugate base, which means the acid that generated it was a stronger acid. If you understand these trends, that's going to be huge in your understanding of organic chemistry, which many of you have to go on and take next year. So the Arrhenius definition is a pretty limited, narrow definition. It really says that an acid is only something that contributes H plus to solution, and a base is something that contributes OH minus to solution. So classic things like hydrochloric acid and sodium hydroxide fit very well. But there's lots of things that we know to be acids or bases that don't fit that. For example, we know amines are bases, but they don't fit that category. So the Bronsted-Lowry definition expands our understanding of what can be an acid or a base. We still define acids as things that contribute protons to solution, but now we say that bases are anything that are capable of accepting a proton. So it has nothing to do with hydroxide, it's just something that can accept a proton. So it expands our definitions. Now, beyond this, we have an even more inclusive definition of what constitutes an acid or a base when we think about the Lewis acid-base definition. So an acid is anything that can accept an electron pair, and a base is anything that can donate an electron pair. And I'm going to go through some examples here, but understanding this concept is, again, one of those really important things to understanding organic chemistry. So being able to understand that something is either electron rich or electron deficient. So Lewis acids we define as things that are electron deficient because they're willing to accept a pair of electrons to form a bond. Now they have to have a vacant orbital to accept that, and protons are absolutely willing to accept a lone pair. So that's why a proton, by all of these definitions, is going to be an acid. But this includes things like atoms with incomplete octets. So remember when we drew things like BF3, when we drew our Lewis structures, this has an incomplete octet, which it's happy having that, but that also makes it very reactive and willing to accept a lone pair, from this example as a Lewis base in nitrogen, having a pair of electrons that it's willing to donate to make a bond. Similarly, we can look at things that have multiple bonds. So looking at SO2 as an example, but here's another example with carbon dioxide. So carbon dioxide, in having this partially positive carbon atom here with this dipole, can be very reactive with oxide here as a base. So this has a pair of electrons that it's willing to donate, and so we've got this electron deficient carbon atom here that allows us to generate this adduct that we see here. Okay, so that's Lewis acids. Lewis bases we define as anything that's electron rich, anything that has a pair of electrons that it can donate to form a bond. So you must have a pair of electrons, but amines here are going to easily classify as Lewis bases. But again, remembering every acid base reaction has both an acid and a base. So we could even think about hydroxide in water here serving as a Lewis base here. So in this case, we're going to have HCl serving as our Lewis acid, and we're going to have water here serving as our base. So lots of ways that we can kind of expand how we think about acids and bases and wrap up our unit here on acids and bases.